Last time we left off talking about acids and the equilibrium constant for acids and how to use that K sub A in calculations. So today we're just going to pick up looking at the base side of those calculations and doing a brief review to bring that back into the front of your mind. So remember, when talking about bases, we had two definitions right now that we're working with. The first original definition that we knew was that a base was anything that reacted with water to produce hydroxide ions. That was the Arrhenius definition. And then we went and made our definition a bit more general with the Bronsted-Lowry definition, and said that a base is just anything that accepts protons in solution. So for this example reaction on this slide of ammonia reacting with water, we can identify ammonia as the base here because its product, on the product side of the equation, it has one more H than it did in the reactant side. It picked up a proton, a hydrogen ion, so it was the proton acceptor. Its base is on the reactant side. When it picks up an additional H, the product that is formed is its conjugate acid, so they are a pair. The water here then is acting as the acid for this reaction. It is donating a hydrogen, donating one of its protons, and then on the product side, what's left is its conjugate base. It's a hydroxide ion. It's missing one of its protons. And so just like before, when we had acids, we can write an equilibrium expression for these reactions. So up at the top, we've got the general equation for the reaction of any base with water. And anytime a base reacts with water, it's going to pick up one hydrogen from the water. So the water has one less hydrogen, the base has one more. These conjugate acid-base pairs will only ever differ by one hydrogen. And again, just like before, we can write an equilibrium expression for this reaction. Instead of Ka, we have Kb, since it's for a base, but it's still the concentration of the products over the concentration of the reactants. Notice, of course, we've only included the aqueous substances here. Water is left out because it's a pure substance, it's a liquid, doesn't have a concentration. Alright, so this is our base dissociation constant, and we can use this just in the exact same ways we used the acid dissociation constant. Here are a couple of examples of weak bases. This table's just here as a reference for you, really, but it shows you the name of the base, its Lewis structure, the conjugate acid that will form when it picks up an additional hydrogen, its reaction with water, you can see they're all producing hydroxide ions, and its base dissociation constant. Notice something interesting about all these bases, maybe something they have in common. They've all got some lone pairs of electrons on them. A lot of them have nitrogen. We'll come back to those observations a bit later. So a couple of generalizations, a couple rules that you can keep in mind regarding weak bases is that any base has to have some source of negative charges because it has to be able to attract the extra proton to it. If it's going to be a proton acceptor, it has to have something to pull those protons in. Now typically this is in the form of lone pairs of electrons, just like we saw on that table above. Any base that we can find is going to have a lone pair somewhere on it, and this is its source of negative charges to pull in the extra proton. A lot of our neutral weak bases contain nitrogen as a general trend. Amines are a class of substances. These are related to ammonia. They're substances that have one or more NH bonds, nitrogen-hydrogen bonds. that get replaced with NC bonds, nitrogen and carbon bonds. So for example, methylamine CH3NH2 has NH bonds and NC bonds. One other trend, the anion of a weak acid is also a weak base. So the leftover, whatever is left over when a weak acid donates its proton, is a conjugate base, and it is also a weak base. Weak acids tend to have weak bases, and we'll see why that trend exists in a second here as well. So for example, we've got HClO here. This is a weak acid. After it donates its proton, the anion that is left is a weak base, and you can see that reaction between the weak base and the water below here. Its base dissociation constant is 3.3 times 10 to the negative 7th, so it falls into our weak base category. Now, to review real quick the types of calculations we can do with these, if you've got your base dissociation constant, you can use an ICE table to calculate your equilibrium concentration of hydroxide ions, and then you could use that to find your pH, your pOH, your concentration of hydrogen, any of those other information from that. So there's two examples down here for you to try. You can pause here and try and do them from memory. We're given the starting concentration of some bases as well as the base dissociation constant. So you can pause and try. I'm going to put the answers up for both of these examples in a second, and then I'll walk through the first one. Alright, so if you tried these in your notes, these are the answers you should have gotten. If you did and you had no trouble, you can skip ahead for the next couple of minutes. If you want the extra review, we'll walk through the steps you should have taken for this first example. So you can go back and then try it for the second later if you want. So the first example wanted to know the pH of a solution that was 0.15 molar NH3. So the first thing we need is a balanced equation for this reaction. So we've got a solution of ammonia. It's 0.15 molar. So it's ammonia dissolved in water. So we've got our reactants over here. We know that ammonia is going to act as our base, pick up an extra hydrogen from the water, giving us NH4 and hydroxide. And again, we can write our equilibrium expression here. We know it's products over reactants, and we were given that value. We know that the base dissociation constant is 1.8 times 10 to the negative 5th. So we've got all the information we need here to create our ICE table. So our initial concentration of NH3 is 0.15 molar, and initially we have 0 product. We're waiting for it to react with the water. Now when that reaction happens, some of the NH3 is going to dissociate, so it's going to decrease in concentration by some amount X. And however much it decreases, however much it dissociates, we will see that same amount, that same magnitude of increase in our NH4 and our OH. The stoichiometry of our reaction is all 1-to-1. So however many of these react and dissociate is equal to the number of products they produce. And then we can get our equilibrium values down here for our table. The products, of course, are easy, 0 plus X. Their concentration at equilibrium is going to be X. The reactant is where we have to remember this assumption we can make here. We are initially going to assume that X, our change in concentration, is very, very small compared to the initial concentration. Since this is a weak base, we're going to assume that it is not dissociating all that much in water. So we're assuming that since this number is so small, the equilibrium concentration is going to be essentially the same. If you think about this being 0.15, if x changed by 0.000005 and you subtracted that from 0.15, by the time you rounded back to two significant figures, you'd have the same number. So that's why we can make that assumption. And of course, we're going to check it. Remember, the rule is that if x comes out to be more than 5% of our initial concentration, we can't hold this assumption. We'll have to go back, plug in the full 0.15 minus x into our expression, and solve a quadratic equation. But it's worth making the assumption to try and do the shorter version of the problem first, since most times it will work. Alright, so here's our ICE table. This gives us all the information we need to plug into our equilibrium expression for Kb. So we had the products over the reactants. Each product has a concentration of x. We've got x squared over 0.15 equals our base dissociation constant. And then we can solve this for x with just a little bit of algebra. Remember, when we finish these problems now, we do need to go back and make sure that our assumption was valid. And in this case, the x that we calculated is indeed less than 5% of 0.15, so we can keep this answer. Quadratic equation avoided. And to finish it off, knowing now the concentration of hydroxide ions is that number we calculated, 1.6 times 10 to the negative third, we can solve for our pOH using our logarithmic formula. We plug in our concentration of OH. We've got our pOH 2.8. And knowing that pH is 14 minus pOH, we also have our pH value greater than 7. So very basic, as we should expect. Now, we've talked about a Ka and a Kb, and as you might expect, these do have a pretty close relationship. If we are considering an acid and its conjugate base, we could have an equilibrium constant for each part of that pair. So to go back to last unit, we already know this rule, that when we add two reactions together, if we've got two intermediate steps or two elementary reactions that we added together to give us an overall reaction, previously we could also solve for the equilibrium constant of that overall third reaction by multiplying the equilibrium constants of the first two. This here is something we've done before. We add up two reactions to get an overall. We multiply their equilibrium constants to get the overall equilibrium constant. So that's old news. The new thing to think about is what happens when these reactions 1 and 2 are a conjugate acid-base pair. Well, in that case, if we've got our acid reaction and the conjugate base reaction added together, the equilibrium or dissociation constants are going to equal our constant for water. So in other words, the larger that Ka is, the smaller the Kb has to be. This is why we've got this relationship that the stronger the acid, the weaker the conjugate base. Strong acids will have weak or negligible conjugate bases. Weak acids will have weak to strong conjugate bases. They will always be related like this. Another way to express this is by taking the negative logarithms of both, so having our pKw is equal to our pKa plus our pKb. And here's just a table to demonstrate that principle at work. As you can see, if we've got a strong acid, in this case HNO3, The conjugate base is negligible. It's so weak, it's not significant. But then as we go through our acids here, as this number gets smaller and smaller, so as our acid gets weaker, the conjugate base is getting stronger. This number is getting bigger. And that's because of the relationship we have to have between these pairs.